What are the factors affecting the speed of waves? The speed of a transverse wave in a string V depends on two factors. The first one is the tension of the string, 張力 T, and the other factor is the mass per unit length of the string. In fact, the equation for speed of a transverse wave in a string V is equal to square root of T over mu, where mu is the mass per unit length of the string. Secondly, the speed of water wave depends only on the water depth, 水深 H. For greater water depth, that means if the water depth increases, the speed of the water wave also increases. Thirdly, the speed of sound wave depends on the medium in which the wave is traveling. If the wave is traveling in air, the speed of sound wave in air is about 330 meters per second. If the sound wave is traveling in water, then the speed of sound wave in water is about 1,500 meters per second. If the sound wave is traveling in solid, for example, in a metal, the speed of sound wave is about 3,000 meters per second. It should be noted that the speed of wave is independent on the frequency of the wave. By the equation, speed of wave equal to the product of frequency of the wave and the wavelength of the wave. If the frequency of the wave is double, that means f pi becomes 2f. Since speed is independent of frequency, the speed of the wave remains constant. Therefore, the wavelength of the wave will be halved. On the other hand, if the frequency of the wave is halved, that means f double pi is equal to f over 2. Since the speed of the wave is independent of frequency, therefore the speed of the wave v remains constant. As a result, the new wavelength of the wave lambda double pi will be doubled. Let's see how speed of the wave v varies with the frequency of the wave using this graph. Since speed of the wave is independent of the frequency, therefore the graph of v against f is a straight line, which makes v the constant value, which is independent of the change of frequency. Let's see how the frequency of the wave varies with the wavelength of the wave, f against lambda. Since the product of f lambda is v, which is a constant, therefore f is inversely proportional to lambda. And we have a graph like this one. Lastly, for the graph of f against 1 over lambda, we will get a straight line passing through the origin, and the slope of this graph is equal to F over 1 over lambda, which is equal to F lambda, which is equal to the speed of the wave. Now look at question number 1. There are 1, 2, 3 complete waves produced at a time of 0.3 seconds. Therefore, the period is equal to 0.3 over 3, which is equal to 0.1 second, and frequency equal to 1 over period equal to 1 over 0.1 equal to 10 Hertz. And the wavelength of the wave is found by 12 over 3, which is equal to 4 cm. Therefore, the wave speed v equal to F lambda equal to 10 times 4, which is 40 cm per second. From the time 0.3 seconds to 0.4 seconds, the time interval is 0.1 second, which is equal to 1 period's time. During a time interval of 1 period's time, the particles along PQ make one oscillation. Therefore, they return to their original positions. Moreover, after a further time of 0.1 second, which is 1 period's time, the wave will move forward a distance of 1 complete wave. Therefore, there should be 1 complete wave longer in length. Therefore, at t equal to 0.4 seconds, the wave pattern will be represented by the blue lines. Now, look at question number 2. After a time of a quarter of period, the particles B, C, D, E, F, G, H has made 1 quarter oscillation, and the new position of these particles will be B, C, D, E, F, G, and H. Therefore, the new wave pattern will be this one. After a time of half a period, all the particles has made 1/2 oscillation. Therefore, the new positions of B to H will be B, C, D, E, F, G, H. Therefore, the new wave pattern will be this like this wave. Now look at question number 3. Since the wave is traveling to the right, the subsequent motion of particle P in a time of 1 period will be upward, downward, and then upward. Therefore, the displacement time graph for particle P in a time of 1 period will be this one. On the other hand, the motion of particle Q in a time of 1 period will be downward, upward, and then downward. Therefore, the displacement time graph for particle Q will be this one. And for particle R, the motion of particle R in a time of 1 period will be downward and then upward. Therefore, the graph of displacement against time for particle R will be this one. Also, note that particles P and Q are anti-phase. And particles R and particles, maybe this one, X, are in phase. Look at question number 4. There are 1, 2, 3.5 wave. Therefore, the wavelength is equal to 14 over 3.5, which is equal to 4 cm. Therefore, the wave speed v equal to f lambda equal to 50 times 4 equal to 200 cm per second or 2 meter per second. For part B, since we learned that wave speed is independent of frequency, even though the frequency increases to 100 Hz, the wave speed remains the same, which is equal to 2 meters per second. The new wavelength lambda will be equal to wave speed v over the new frequency, which is equal to 200 cm per second over 100 equal to 2 cm. That means the wavelength is halved. Therefore, the new wave length will be